Hello, welcome to our lectures on electromagnetism. We're going to start with Gauss's law, but we'll touch upon Coulomb's law. I'm not going to go into depth with that because it's pretty basic concepts, to be honest. Now, we should all know that like charges repel and opposite charges attract. And we'll start with the definition of electric field. The electric field is the electric force per unit charge, which is given by here, where F is the electric force on a charge Q at a point R. The electric field is a vector field that has a magnitude and direction at all values of R. Now Q, on an added note, Q is often called a test charge because it tests the electric field vector. Now we take the test charge to be small enough as to not cause a disturbance to the field. In Cartesian coordinates, the electric field is here. Now, the field lines, by convention, we take positive to be sources and negatives to be sinks. Well, this is just by convention. There's no real law of the universe that says that a positive must be a source and a negative must be a sinks. We could call the negative what is the positive, vice versa. I won't go much into that. Now, the principle of superposition. This is how the field lines would intersect if the charges were opposite, and this is how they would repel. Opposite. This is how they would repel one another if they were two like charges. Anyway, the principle of superposition states that the electric field due to a set of sources is equal to the vector sum of the individual electric fields due to each source. Now, symmetry principle for electric fields. Any operation that leaves the sources of an electric field unchanged also leaves the field unchanged. The field inherits the symmetry of its sources. Now, electric charge allows particles to exert and experience electromagnetic forces. Electric charge is a scalar quantity that is additive. Quantized, locally conserved and invariant. A stationary point charge experiences an electric force but not a magnetic one. A moving charge experiences the same electric force as a stationary charge, and a force is a result of being in motion, which is classified as a magnetic force. Electric forces between stationary charges are called electrostatic. The electrostatic force between two charges, Q1 and Q2, separated by a distance R12, is given by Coulomb's law, which is here, where F12 is the force acting on particle 1 due to particle 2, and here is the permittivity of free space. The definition of a charge density. To determine the charge density, rho of R at a point, at a point R, we take a small volume element centered on the point R and divide by the charge delta Q within the element by its volume delta V. For an infinitesimally small volume, the charge density becomes a differential dQ by dV. Now, this is Coulomb's law for a multiple charges here. I just thought I would add that in. Now, calculating the total charge in a region from a charge density function and finding the total charge Q within the region V by integrating the charge density function, where dq over dv, where the integral here, Q, is the integral of the charge density over the volume, where this is a volume integral. The definition of electric flux through a plane, the element here, where this is a orientated plane element, and the definition of a flux through a surface is given here. And we go from Coulomb's law to integral Gauss's. Now, this is Coulomb's law. We consider a sphere of radius r centered on a stationary point Q at the origin. The sphere forms a closed surface S. Unit normal points outward. E is given here, the electric field, shown that my point on S, the unit normal component produced by the point charge Q, the electric flux, and since the normal is constant over the surface of the sphere, the required surface integral is obtained by multiplying this component by the surface area 4 pi r squared that is given here, and this would be Gauss's law. Well, we're getting on. This is the right hand side of Gauss's law. Now, Gauss's law, the electric flux over any closed surface S is equal to the total charge enclosed by the surface divided by the permittivity of free space that is here. The surface we're using as a mathematical object is often called a Gaussian surface. Anyway, this law is true for all closed surfaces irrespective of the shape, and for all distributions of charge whether they are stationary or not. Any charge outside the surface makes no contribution to the electric flux over the surface. Gauss's law does not apply to open surfaces because the concept of total charge only makes sense for a surface that's enclosed. Now, Gauss's law is stated here, where S is a surface and V is the volume inside. Now, a spherical symmetry. For a uniform distribution of positive charge Q occupying a sphere of radius r centered on the origin, so the electric field also has spherical symmetry, and its magnitude can only depend on a distance to the center, E sub r. To determine ER outside the sphere of charge, we exploit symmetry, and a spherical Gaussian sphere centered at the origin where lowercase r is greater than uppercase r. This contains the whole charge distribution, so encloses a total charge Q. So, which gives this here, Gauss's law. The differential form, ds, is here, the differential area, and integrating over this through 0 to pi and 0 to 2 pi gives here. And now for inside the sphere, where lowercase r is less than uppercase r, rho equals this, the charge density. So we're just dividing by the volumes, and we come to this with the directional vector er. Now, for cylindrical symmetry, the Gaussian must be enclosed, so it has two end faces. The electric field is radial, so it is parallel to the end faces of the Gaussian surface, therefore they contribute no flux. The curved part of the Gaussian has area 2 pi r delta L. The electric field is perpendicular to this surface and has a constant normal over it, so the flux of the curved surface is ER 2 pi r delta L. The total charge enclosed by the Gaussian surface is lambda delta L. So by Gauss's law, we end up with this. Now, in planar symmetry, the definition of a surface charge density, to determine the charge density at a point R on a plane, we take a small area element centered on R and divide by delta Q across the area element by delta A. For an infinitesimally small area element, the surface charge density becomes the differential Q by dA. The definition of a uniform plane of charge as the same charge density across its infinite area. However, charge density can also be used to characterize a non-uniform distribution of charge. The electric field of a uniform plane of charge has considerable symmetry, is perpendicular to the plane and does not vary in any direction parallel to the plane, and is reversed by reflection. Now, an example. We take a Gaussian surface, which is this cylindrical shape in a plane. Now, by Gauss's law, we have this, which is really straightforward, where n is a unit normal vector pointing perpendicular away from the plane. Now for a parallel plate capacitor, parallel plates separated by a narrow gap which is empty. Yeah, suppose you want to know the electric field inside and just outside. If you keep away from the edges, you are either in the gap or outside, but close. Then any edge effects can be ignored. This means you can treat the plates of the capacitor as if they were two plates of charge with uniform surface charge densities, sigma q over a and negative sigma over a. So the electric field is found using E equals the sigma over 2 and the permittivity of free space. And with the principle of superposition, the electric field at a plane does not decrease with distance. Hence, two planes produce same magnitude outside and as opposite directions, so they cancel out. So the electric field in the gap is this. Now, differential Gausses. And this gives a relationship between electric field and charge density at a single point in space, which is the divergence here. Calculating the electric field inside a charged insulating slab. An insulating non-conducting slab lies between Z equals minus d over 2 and Z equals plus d over 2 and is infinite in x and y. The slab has a uniform charge density rho naught, which is isolated from all other influences. Therefore, electric field for Z greater than 0 is the reverse of the field for 0 is greater than Z. Now, using differential Gausses, we'll find the electric field in the slab by planar symmetry here, which this is the divergence. And this is just the regular right side of Gauss's, which gives the differential of E of Z rho over epsilon naught. Integrating both sides, we get this, where C is a constant of integration. We have reflection or symmetry at a point Z equals 0, so E sub Z equals minus E sub Z, which implies that plus C and plus C here, minus, so C equals 0. Yeah, so sorry, let me just write this out. So the minuses would cancel, so both sides equal, so that means C is 0, and E sub Z equals rho naught of Z over epsilon naught, which this is the right hand side of Gauss's law. I think that's it. Yes, thank you for watching, and please do subscribe.